Okay, so welcome everybody. Welcome to the latest edition of this MetaMAT webinar series. So this week I have the pleasure of introducing Dr. Alice Vanel. So Alice is an expert in the mathematical modeling of wave propagation in complex media. So she works on applications to emergent fields such as acoustic metamaterials, phononic crystals, and plasmonic resonant nanoparticles. So she did her PhD here at Imperial College under the supervision of Richard Kroster and Uri Schnitzer, before then moving to ETH to become a postdoc in the group of Habib Mari. So today she's going to talk about modal approximations for plasmonic resonators in the time domain and applications to super-localisation. So on that note, Alice, over to you.
Good afternoon, everyone. Thank you, Bryn, for the introduction. I first would like to thank you all for attending this talk, and thank you, Bogdan, Sebastian, Moemer, for the invitation to the webinar. So my name is Alice, and the work I want to present today was done in collaboration with Lorenzo, who was a PhD student at ETH and is now doing a postdoc in Texas. And he did most of the coding for all the numerics. So thanks a lot, Lorenzo. It looks much better with the numerics. Pierre, who works in Paris at Institut Langevin, and Habib Mari, who was my advisor at ETH. And today the question I would like to address is it possible to derive a modal approximation of the field scattered by a plasmonic nanoparticle? So if we excite a small metallic particle that has dispersive parameters, can we describe the interaction of light with the particle efficiently and accurately? So the main part of this talk is going to be concerned with the framework we developed to derive such approximations. And in the second part of this talk, what are the applications of such methods? Oh. Okay. So the first, the motivation. Why is this important? So modal expansions, they are widely used in the physics community. They have numerous advantages. The modes are very easily computed because they are solution to a source-free problem. They are intrinsic quantities of the system, and they give a good physical insight into what's happening. And when the domain is closed and bounded, and we have the Helmholtz equation, it's relatively easy to obtain such a modal decomposition. Because the system is Hermitian, we can apply this, the spectral theorem. We get real eigenvalues and a complete basis of eigenmodes that are solutions to the source-free problem. And once the modes are calculated, the response of the system to any excitation can be achieved at a low computational cost. So it's a very attractive method. However, when we have an open system, so like an exterior problem, it's a lot more difficult because the radiation condition is not adjoint and it becomes an inwards condition, which is not physical. The system is not Hermitian. We can't apply the spectral theorem. The eigenvalues are complex, which means that if we choose them so that they decay in space, they grow in time. Which is not physical. This is known in the literature as Lamb's exponential catastrophe. Recently, some groups have introduced renormalization techniques. And the question we want to answer today is how do we work around these difficulties? Can we still decompose the field in a basis of eigenmodes? And the way we work around this is that we use the smallness of the particle to derive an approximation in the quasi-static regime. We diagonalize our system at frequency 0, and then we use perturbation analysis to get a modal approximation valid for low frequencies. So the talk today is structured as follows. We start with the scalar case. So the Helmholtz equation in 2 and 3 dimensions. This part will be quite detailed and analytical and will take a good part of the hour. During the second part, we show numerical simulations to validate the main theorems of the first part. In the third part, we look very briefly at Maxwell's equations. We don't really go into details here. I just want to point out the main difference with the scalar case and the main difficulties we encounter. And finally, in the last section, we look at one application, which is the super-localization of an emitter that's placed close to a nanoparticle. In this case, there's something happening called a mirage, which means that when we try to localize the emitter, it's really hard to find it because it's coupling with the nanoparticle. And in that part of the talk, we are going to see how the modal expansion we derived in the first part helps us to localize the particle. Okay, so let us begin with the scalar case. We consider a particle D centered at Z that has size delta. It's placed in a homogeneous medium with permittivity epsilon m and permeability epsilon c. Sorry, the medium and permeability epsilon mu m. The particle is metallic, so it has frequency-dependent permittivity epsilon c. We choose the Drude model for the permittivity, quite classical, and we define a contrast parameter lambda. And these models the transverse magnetic polarization. So the governing equations are the Helmholtz equation. So here D can be 2 or 3. This is valid in 2 and 3 dimensions. We have Sommerfeld radiation conditions at infinity. And we have jump conditions on the boundary of the particle. So U is continuous across the boundary, but its normal derivative has a jump because of the different permittivities. And the goal is to solve this system of equations and obtain a solution in the form U scattered, so U minus the incident field, as a sum of weighted modes, where alpha n's are the weights and Vn are the modes. And we want to take advantage of the size of the particle to obtain such a solution. So here, what we call a low frequency regime is actually the long wavelength regime. So what matters is that the size of the particle is very small compared to the wavelength. So for our applications in the visible range, we want the lambda to be between 400 and 700 nanometers, which corresponds to frequencies that are between 400 and 700 terahertz. So the orders of magnitude to keep in mind for the rest of the talk is that delta is a few tens of nanometers, and the frequency is quite large, 10 to the power 15 hertz, which is why, I mean, it is low frequency, but it's quite a large number. So we define a non-dimensional small asymptotic parameter, which is delta times omega over c, and it's roughly 10 to the minus 2. A classical way to solve this system of equation is to use boundary integral equations. It's quite common in scattering theory, and it's very relevant for numerical applications because we reduce the domain, the dimension of the domain to be discretized is reduced by 1 because we only work on the boundary. So it turns a 3D problem into a 2D problem and a 2D problem into a 1D problem. And for that, we need to define the Green's function for Helmholtz equation. So it's the unique solution of delta plus k squared with a Dirac on the right-hand side. And in 3D, it's given by the complex exponential, and in 2D by the Henkel function. And with that Green's function, we define the two important boundary integral operators, which are the single layer potential, which maps a potential phi into the integral over the boundary of our domain times the Green's function times the density, and the Neumann-Poincaré operator, which called k star, which maps a density to the normal derivative of the Green's function times the density. One of the most important relations between the single layer and the Norman Poincare operator is these trace relations. So the single layer potential is continuous across the boundary. There's no jump, but its normal derivative has a jump, and that jump involves k star. And from that, we already get the idea that expressing the field as the single layer potential of a density is going to work out because U also has a jump across the boundary. So we transform our problem into a boundary problem by introducing two unknown densities, phi and psi. So we say that U is the single layer potential of phi inside the particle, where the wave number is Kc, and because it's metal, and then outside of the particle, it's the incident field plus the single layer potential with Km this time of another density psi. And now we have two unknowns, psi and phi, and they are the unique solution of that system. So we obtain that system by plugging that U in the governing equations, the Helmholtz equation with all the jump conditions. To take advantage of the smallness of the particle, we need to rescale our problem. So for that, we define a non-dimensional large X, which is going to be of size 1. So small x is Z, the center of the particle, plus delta times big X. And now our particle D can be Z plus delta B, where B is at the origin and has size 1. And now for each function on the boundary of D, we can define a corresponding function on the boundary of B. So we rescale on that, and we rescale our equations. For that, we have very well-known scaling properties of the integral operators. And that helps us because the single layer potential is invertible for small frequencies. And once we've inverted the single layer potential, we can get phi re-inject in the second equation, and we get a unique equation satisfied by the one density psi. So it's a complicated operator A that depends on the frequency of psi equals F. And F here is a function of the incoming field, so you should think of it as a complicated function of the incoming wave. The problem is that this operator is not self-adjoint in L2, so we can't directly diagonalize it to solve the equation. However, we can do Taylor expansions and try to see if it simplifies. So we just by Taylor expanding, we have expansion. So this is in 3D of the Norman Poincare operator of the single layer potential and its inverse. And once we've developed all that, we obtain a hierarchy of equations in power of delta omega over C. And then we get, depending whether it's 2D or 3D, so in 2D it's quite similar, but we usually have logarithms. We get an expansion of the operator A, and what's important to see here is that the leading order, A0, can be expressed very simply in terms of the Norman Poincare operator. And that's going to help us because in some spaces, the Norman Poincare operator can be inverted. So just a tiny bit of functional analysis. We call H1/2 the usual Sobolev space and H-1/2 the dual space. And then we can define H star, which is H-1/2, equipped with a new inner product. And in 3D, the inner product is simply minus U times single layer potential at frequency 0, so just the static one. Between -1/2 and 1/2, so just the integral over the boundary of U times a single layer potential of V. And that new space H star is very important in this analysis because the Norman Poincaré operator is self-adjoint in that with that inner product. And because it's compact and the spectrum is discrete, and then we can apply our spectral theorem and diagonalize K star. So now we can express K star as the sum between j equals 0 and infinity of lambda j times the inner product with phi j times phi j. So here lambda j's and phi j's are the eigenvalues and the eigenvectors of K star. And the known properties of these eigenvalues is that they are between -1/2 and 1/2. Lambda 0 is 1/2, and they all accumulate at 0. And because A0 can be expressed simply in terms of KB star, now we can also diagonalize AB0 as the sum between j is 0 and infinity of tau j times the inner product times phi j, where tau j is a simple function of the contrast lambda of omega and the eigenvalues of KB star. And from that we can derive static modal expansion. So we can say that at frequency 0, the field is going to be the sum between 0 and infinity of 1 over tau j times f, which is a function of the incoming field, the inner product with phi, times the single layer potential. And this is not very useful in our case because we want a time domain approximation of the field, and so we need something that's frequency dependent. So how do we derive instead a quasi-static approximation? And if we were to do a classic Taylor expansion of when inverting a operator A of phi is f, the problem is that because the eigenvalues accumulate at 0 and there's an infinity of them, the validity range of our expansion would vanish at infinity, and it wouldn't be uniform. So in order to get a meaningful expansion, we need to work with a finite number of modes. The other reason for that is that because we want to take a Fourier transform, we also need it's quite complex to apply the residue theorem with an infinite number of eigenvalues. So that's another reason why we need to truncate our sum. It's been empirically reported that actually only a few modes contribute to the scattered field. So in all the experiments and all the numerical simulations that have been done, we kind of know that we never have an infinity of modes that radiate. And it's quite easy to understand if we think of that these modes are eigenmodes of a pseudo differential operator of order -1. That's K star. And they are oscillating functions. And if you think of Fourier analysis, where the decay of the coefficients is determined by the regularity, it tells us here that the more f and phi vary over the boundary, if f is smooth, we can expect a fast decay of the coefficients. Some work has been done on these higher order modes. In the paper written by Ori Schnitzer called Geometric Quantization of Localized Surface Plasmons, he quantified the oscillation rates for smooth axisymmetric inclusions, and he proved that the contribution of higher order modes to the electric field outside of the particle decays exponentially in space. And in a even more recent paper by Ando called Surface Localization of Plasmons in 3-dimensional convexity, he proved the exponential decay of the single layer potential of the mode far away from the particle when j goes to infinity. So with these results, we have good reasons to believe that these we don't need to take all the sum in this all the terms in this sum. The coefficients seem to decay, and the modes themselves seem to decay. However, we can't use these results as they are because they are just using the static modes, and we want to use dynamic modes. So ideally, we would want that sum to have tau j of omega, so a frequency-dependent resonance, and the single layer to also depend on the frequency. One of the main results is that if we take, so that's all in 3 dimensions. If we take our particle to be strictly convex and have a smooth boundary, we're able to prove that the inner product between f and phi's is a small o of the index j to the power minus big J over 4. So if f is smooth enough, so in a Sobolev space of order j. I'm not going to go into the details of that proof because it's long and technical, but it's all in a paper. So if you're interested, I'll give the references at the end of the talk. I'll just give the main 2 results that we used to prove this. And they are from a paper the same paper by Ando, surface localization of plasmons in 3-dimensional convexity, that shows that we can modify our Neumann-Poincaré operator into another operator that has nice properties, and a paper from Miyanishi, eigenvalues of the Neumann-Poincaré operator in dimension 3, that calculates the decay rate of the Neumann-Poincaré's operator's eigenvalues. And using these 2 quite recent results, we prove that our inner products have a super polynomial decay. And that allows us to truncate the sum. In 2 dimensions, the picture is quite different. The eigenvalues decay a lot faster. So they decay like j to the minus, they have exponential decay, whereas in our case, it's just 1 over square root j. However, there's an infinite number of negative eigenvalues. And k star cannot be modified into a positive definite operator like we've done in 3D. There's been some work done by Habib Amari's group on algebraic domains, and they've shown that there's a finite number of plasmonic resonances, but we are not able to prove a similar result in 2D. And so from now on, our particle B is strictly convex and has a C-infinity smooth boundary to allow for the truncation. And so now we can assume that F can be expressed in the truncated basis of modes. And it gives us a spectral decomposition of the field in the quasi-static regime. U scattered is the sum between 0 and j of 1 over tau j times the inner product between the incoming field and phi times the single layer potential of phi. The tau j's, they are perturbation of the static ones. So depending on whether it's 2D or 3D, they come from the expansion of the operator A. The single layer potential of phi, they are the generalized modes of our system. And the phi's, they are orthogonal in the space H star. And when tau j is very small, and if the inner product is not 0, then these modes are excited and they propagate into the far field. In 3D, we can calculate them explicitly, the first order corrected plasmonic resonances. They depend on the size. They are bounded, and this allows us to define a resonance radius. So this R delta, which is the max of these 2 terms. This resonance radius is large enough to encompass all the resonances, and it corresponds to a quasi-static regime. And it gives our method a range of validity because, for example, if we fix that R of delta times delta divided by C is smaller than 1/2, we make sure that we are always in the quasi-static regime. So we are now ready to take the Fourier transform of our modal expansion to get the expansion in the time domain. Because our expansion is only valid in the quasi-static regime, we can't take a full Fourier transform. We don't really know what the field behaves like outside of the quasi-static regime. So we only take the Fourier transform between, so we fix a positive rho and we take only the Fourier transform between minus rho and rho where we know what the scattered field is like. And we defined T0 to be the time it takes for the particle, for the, the excitation to reach the particle and get to the observation point. So from now on, S is the source, Z is still the center, X is our observation point. And 2 delta, this plus or minus 2 delta accounts for what happens in the particle. And the main result is that the scattered field has the following form in the time domain. So when T is smaller than T0 minus, it's just a reminder. Of course, it's a causal system. So if we could take the full Fourier transform, we would get 0 here. So that reminder doesn't really have a physical meaning. And when T is bigger than T0 plus, the field is the sum from 1 to j of a constant that only depends on the index, the size, and the permittivity model times the inner product between the modes and the incoming wave times the single layer potential of the modes times an exponential plus a reminder once again. A few important things here. The imaginary part of the plasmonic resonance frequencies is negative. So we are summing decaying oscillations in time. The imaginary part actually accounts for the absorption and radiation losses in the particle. And since our, as I said, we had to compute here a truncated Fourier transform, which means we have reminders that we shouldn't have. But when delta goes to 0, they go fast to 0. How do we prove this? It's just a Fourier transform and a residue theorem. I don't think I will go into the details of these slides, but basically if you look at the bottom picture, all the resonances are in the lower part of the complex plane. The main contribution of the scattered field comes from integrating around these poles. And everything on the boundary goes inside the remainder. All this is to prove that the remainders are small. I think I will just skip that part because I don't have much time. So let's move on to the next part, which is numerical simulations. All the numerical simulations have been done in 2D. I haven't shown the theorems for 2D. They are very similar to the 3D ones, just with a few logarithms. This is the setting. So the goal of this section is to illustrate the validity of the approach and show that the approximation seems to be working with less restrictive hypotheses than the ones in our theorem. They work, as you will see in the next slide, they work for more general shapes. So we can even take non-convex and non-algebraic shapes, and they also work when we are quite close to the particle. So we don't really need a far-field approximation. So here we sketch the simulation setting with the ellipse. We define four observation points, three that are close to the particle. So here we take the ellipse to be 50 × 10 nanometers. And the observation points to be just 150 nanometers away from the origin. So these observation points are in the almost near field. And then we choose a point D that's 3000 nanometers away from the origin. So that's the far-field approximation. This sketch is not up to scale. Our nanoparticle is illuminated by a plane wave. And f is the Fourier transform of a bump function, compactly supported in the interval 0, C1. And we plot the time domain incoming wave on the right. We will illustrate our results on 3 domains. First, a rounded diamond. It's algebraic of class Q, which is the hypothesis we need for the 2D truncation. And it satisfies all the hypotheses of the theorems. Then we will look at the narrow ellipse, which is algebraic but not of class Q, so we don't really have results on whether we can truncate the sum or not. And finally, we look at the flower, which is neither algebraic nor convex. Numerically, we check that we are allowed to truncate this sum. So the inner product of f times phi j in H star, we can plot it against the index of the modes. And we can see that for the ellipse, the flower of the diamond, it decays. So keep in mind that this is a log scale. It decays a lot faster for the ellipse. And we can already see from here that only 2 modes are going to contribute to the ellipse, which are the 2 dipoles that we know. And we can see that for the flower and the diamond, we are going to need to use a bit more modes. And then we can also verify that the modes, the single layer potential of phi also decays with the index. And because we multiply them together, we expect that even without the hypothesis, everything will be fine. Here we plot the plasmonic resonances for our 3 shapes. We verify that our resonance radius R of delta encompasses all the frequency resonances. And by calculating R delta times delta times divided by C, we double check that we are in the validity range region. It's smaller than 1/2. Now, how do we compute the reference solution so that we can validate the asymptotic solution? It's basically a big discretization. So we discretize the frequency domain with 10,000 points. We compute the scattered field using the representation formula. So what we did in the very first slides. So we need to solve that equation on the boundary of the domain. We need to discretize the single layer. Here we use 2 to the power 8 points, and then we take an inverse Fourier transform. And the computation time for that is linear in L. And now for the asymptotic solution, we simply pre-compute all the modes, and then we sum them. And in general, we've done it with 30 modes, which is more than enough. And here the computation time is linear in J. So the asymptotic solution is at least 100 times faster to compute than the reference solution. And because the modes can be pre-computed, if we choose to change the illumination, the asymptotic solution is really fast to compute again. Whereas for the reference one, we have to do all the computations again. So we begin with the diamond because it's the shape that satisfies all the hypotheses of the theorem. here we measure at D, so in the far field, and we plot the real part of the scattered field against time. So the blue one is the reference solution, and we can see that it's very nicely approximated by the sum of the 4 most important modes for the diamond. And now, if we look at the ellipse, with the ellipse, the modes are a bit more familiar. We have, if we observe close to the narrow apex of the ellipse, we observe that dipole, so the one that radiates right and left. And again, the fit is fine. And if we observe at the 90 degrees angle, we have a different mode, so a slightly slower, frequency, and we get the other ellipse, so the one that radiates vertically. So now what happens if we observe from B? Well, we get a sum of these modes quite predictably. And again, the asymptotic solution is quite good at representing the reference solution. And finally, if we look at the flower, as expected from the slower decay of the coefficients, we need more modes. So actually, to reconstruct 99% of the reference solutions, we need 8. But for a 5% error, 5 were enough. And now the last point is what happens at higher frequencies. So we said that here we've only computed the scattered field in a low frequency regime. What happens if we take if we integrate between higher frequencies? And what we see is that it's the low frequency part of the domain seems to be a very good solution even for higher frequencies. There doesn't seem to be any poles outside of the quasi-static regime. And that's probably due to the dispersive characteristic of the metal that becomes transparent at very high frequencies. So that's the last slide on the numerics. Now we move on to the Maxwell's equations. So for Maxwell's equations, as I said at the beginning, I'm not going to go into details because I don't really have time, and it's a lot of just functional analysis. But the main lines are that we use the Liebman-Schwinger equation satisfied by the electric field. So it's the identity minus another contrast parameter times an operator of the electric field is the incident electric field. So gamma, again, is a nonlinear function of the frequency that depends on the permittivity model. And T here is a singular operator. It's the magnetization integral operator. Unfortunately, T is neither compact nor self-adjoint in L2, but T0, so at 0 frequency, it has nice properties. And we have the following orthogonal decomposition of L2. And T0 is bounded and self-adjoint, and these spaces are invariant, these subspaces. So we follow the same steps as we did in the scalar case. We build a complete basis in the static case. We truncate the modal expansion for a strictly convex and smooth particle. We perform a perturbative analysis. We prove the existence of the poles for the perturbed resolvent, and then we construct the modes and take the Fourier transform. It's the main technical difficulty in this is that these subspaces are only invariant under T0. as soon as we add a frequency, it's no longer invariant, and then it becomes very difficult to control the error on the other subspaces. However, we got to a theorem, and if you're interested, I'll give a link at the end of the talk. And now finally, how can we use these methods to solve a physics problem? Let's apply it to super-localization. So super-resolution imaging has had a big impact on medical imaging. It won a Nobel Prize in 2014, and it managed to reduce the resolution limit from the classical diffraction limit, which was 250 nanometers, to about 20 nanometers. And how microscopy works is that we put an emitter in a diffracted limited spot, and then we try to image it. And in this paper published in Nature Communications by the Rab and his group, called Shifting Molecular Localization by Plasmonic Coupling in a Single Molecule Mirage, they exhibited the fact that when we, so if you look at A, when we image a single molecule, the image is centered at the position of the molecule. But if the molecule is placed to a nanoparticle and there's coupling between the two, then the imaging that you obtain corresponds neither to where the molecule is, neither where the nanoparticle is. And from that, we get a mirage. So can we use what we've done in the first part to correct this mirage and find our emitter? So how do we model this? Most fluorescent emitters behave like ideal electric dipoles. So our setting is very similar to the setting we had in the first part, except that instead of having an incoming wave, our source point, now our source point is a dipole. So our governing equation is Helmholtz on the left-hand side, and on the right-hand side, the dipole forcing. So P star, which is the direction of the dipole, times the gradient of the delta function at Z star, which is what we call the position of our little emitter. And on top of that, we have outgoing radiation conditions at infinity. What we want to be able to do is measure the field U in the far field. So maybe we have sensors on the omega, so like a circle far away from the system, where we measure the scattered field. And from these measurements, we want to be able to reconstruct the position, Z star, and the orientation, P star. Because we are still in a quasi-static regime where the size of the particle times the frequency divided by C is very small compared to 1, we can approximate the scattered field with, let's say, n modes. And we say that the scattered field is the gradient of the Green's function times scalar P star plus a sum of modes that radiate. To achieve the super-localization of the molecule, we need to backpropagate U and maximize the backpropagating function. So let's start with the simpler case where we don't have a resonating particle. Then we define what we call an imaging functional. So an imaging functional is an integral over dBr. Sorry for the inconsistent notation. So here Br is the omega from before. So it's the circle with the receptors where we measure the scattered field. So of the complex conjugate of the gradient of the Green's function times the field. And a classical result in imaging is that this imaging functional has an amplitude peak at the position of the particle, and it's a vector and its orientation is parallel to p star. So if we compute that functional, the maximum will be at z star and it will be parallel to p star. So we find our emitter. Now we define the matrix, the vector product of the complex conjugate of the gradient of the Green's function times the gradient with respect to the other variable of the Green's function. And we know that the limit of R when R, so here the radius of that circle tends to infinity, becomes the identity times a constant. And that helps us define our optimization problem to find Z star and P star. So we can just automate everything with that optimization problem. So we know that Z star and P star are going to be the minimum of the L2 norm in the space where we look for the emitter of I minus R times P. All right, so now when we add the particle, we combine our expansion of U with this imaging functional, and we get a corrected imaging functional. So we just plug in the field U inside the imaging functional that we just defined, and we get that the imaging functional is now R of Z star times P star plus the sum between N and N equals 1 and M. M is the number of modes that we decide to take into account, times an unknown coupling coefficient, times a mode. So it's not exactly the mode we had before, but it's an integral over a boundary of the Green's function times the modes we have before. So this is a pre-computable quantity, and we shouldn't really worry about this. The difficult part here is to find the lambda of Z star. And because, so it is because of that coupling that we obtain a mirage. It's because the little emitter excites the modes of the nanoparticle that it becomes really hard to place. And these coefficients, which are kind of the weights of the modes, they are the ones that help us localize the particle. So now the new optimization problem, which no longer has 4 unknowns, but it has 4 plus m unknowns if we decide to look for m modes, is the minimum of I minus R times P minus the sum between n and 1 and m of lambda n times theta. With Lorenzo, we implemented all this. And we started with the rounded diamond. So here the dipole, the real dipole center is the star. So you see it's in the very near field, very close to the rounded square. And if we use the first imaging functional or just look for the maximum of the field, we would think the mirage would place the emitter here on the large circle. And when we use our corrected imaging, we find the red cross, so a lot closer. So the error we measure here is 19 nanometers without the correction, and it's 10 nanometers after correction. And with the flower, it's even more striking because the error is 29 nanometers before correction and only 8 nanometers after correction. Now in a real setting, we would have sensors placed to measure the field, and that creates white noise. So the last thing we did was to check if our method is stable under noise. So we computed the imaging functionals again when now the data has been corrupted by a Gaussian white noise. So the U that we measure is the U from before plus a random variable that follows a normal law of expectancy 0 and variance sigma, where we can control the strength of the noise with sigma 0. Oh, okay. And this is the result with a 40% noise. The error is 31 nanometers without the correction and only 11 with the new imaging functional. And what we see here is that the corrected imaging functional performs well, even with quite a high level of noise. So this whole method is robust with respect to additive measurement noise. So that's the conclusion of today's talk. A little take-home message. In the framework of plasmonic nanoparticles with regularity and convexity conditions on the domain, modal expansions work. We only need a small number of modes, and the causality principle ensures that the modes do not diverge far away from the particle. The applications are the fast computation of scattering problem solutions, and the one we just saw, the super-localisation of a point-like emitter in the resonant environment. And some possible extensions would be to look at now subwavelength dielectric cavities and particles. The work I've presented today is published in these two papers at the bottom of the slide, if you're interested in the details. I want to thank you all for your attention. If you have any questions, please ask me.
Wonderful, thank you, Alice. Very insightful talk. Modal expansions, everyone likes a modal expansion, but as you explained quite nicely, there are plenty of cases that we care about where it's not trivial at all. So quite influential work here. Does anyone have any questions they'd like to ask Alice?